Okay, this is Math 176, Calculus 2, Lesson 1. So this is the continuation of first year calculus, the second semester, and I'll start with a very brief review of some of the things that were in Math 175, Calculus 1. And the basic thing you learn for most of the semester is differentiation. So if you have a function f of x equal to sine of x, then the derivative is cosine x. If f of x is x squared, then the derivative is 2x. There are alternate notations that you can use for a function. If y is e to the x, dy dx is e to the x. If y is arctangent of x, dy dx is 1 over 1 plus x squared. And a great deal of what you learn in Math 175 is how to differentiate a function, or how to find the derivative. Near the end of the semester of Calc 1, you learned how to go in the opposite direction. The opposite direction is the following problem. Given the derivative, find y. So for example, if dy dx were equal to cosine x, then what function has derivative equal to cosine x? Well, y could be sine of x plus any constant. So instead of starting with the function and finding its derivative, now in the opposite direction, we're given the derivative of a function, and we want to find the function. So this is called finding the antiderivative. Again, the problem is, given the derivative dy dx, find y. So if dy dx equals 1 over 1 plus x squared, then y is arctangent of x plus a constant. Another name for the antiderivative is the indefinite integral. So, and the notation is this curly sign times the function, let's say x to the fourth minus 2x plus 3 dx. This means find the function whose derivative is this fourth degree polynomial. And such a function is 1/5 x to the fifth minus x squared plus 3x plus any constant. This is the antiderivative. And you spent some time near the end of Math 175 learning a little bit how to compute some antiderivatives. And this semester we'll spend quite a bit more time learning techniques of integration. finding the indefinite integral, finding the antiderivative. Now, sometimes you're given additional information about the unknown function that you're trying to find. So for example, you might have the following problem. Find the function y equal f of x such that dy dx is e to the x and f at 0 is, let's say, equal to 3. So what can we say? Well, the antiderivative, or indefinite integral, of e to the x dx, let's call this capital F, capital F, is equal to e to the x plus a constant. That's what we get from knowing that the derivative of y is e to the x. This condition allows us to determine a constant, because if we let x equal 0, f of 0 is e to the 0 plus c. E to the 0 is 1, and this is supposed to equal 3. So that means that c is equal to 2, and the function we're looking for is e to the x plus 2. So this is the antiderivative, or the indefinite integral. There's another problem that uses integration. It's a problem which is very geometrical. Suppose you have a function y equals f of x, which is greater than or equal to 0 for x between a and b. So from a to b, let's say the graph of the function looks something like that. And because the function is non-negative, this graph is above the x-axis, and it's reasonable to ask, what is the area under the curve above the x-axis and bounded on the left by the line x equal a and the right by the line x equal b? So the area under the curve of f of x for x between a and b, well, another name for it is the definite integral. And it's denoted, this integral sign, this curly squiggly thing, but a to b, the lower and the upper limits of integration, f of x dx. So this is the area for a non-negative function. So for example, if we let f of x equal the sine of x for x between 0 and pi, it looks like that. 0, pi, and at pi over 2, it has a maximum value of 1. And let's say we want to find the area under that curve. So that's the integral from 0 to pi of sine of x dx. And what is that equal to? Well, to find that, we need to use what is called the fundamental theorem of calculus. What does that say? So the first form of the fundamental theorem says the following. Suppose we have a function f of x, and we take the antiderivative or the indefinite integral, and we call that function capital F of x. So the fundamental theorem of calculus in its first form says the following. The integral, the definite integral from a to b of f of x dx is just the indefinite integral, capital F, evaluated at b minus capital F evaluated at a. And I'll give that a star because that is a truly important fundamental fact from calculus. This you absolutely, positively must know. So if we go back to the problem of finding the area under the function y equals sine of x from 0 to pi, we take the indefinite integral. What is the indefinite integral of the sine of x? Well, that capital F of x, right? Little f of x is sine of x. The indefinite integral is minus the cosine of x plus any constant. And what we want to find is this area. This is the integral from 0 to pi of sine x dx. That's minus cosine, so that's f of pi minus f of 0. If capital F is the antiderivative, the definite integral is from 0 to pi is capital F of pi minus capital F of 0. What is capital F of pi? Minus cosine pi plus c minus capital F of 0 minus cosine 0 plus c. We see that these constants cancel out. Cosine pi is minus 1, so that's minus minus 1. Minus, let's see, cosine of 0 is 1 minus 1. So that's equal to 1 plus 1, it's 2. So the area is 2. I mean, that's really a very beautiful geometrical result. It would be extremely difficult to find this without calculus. If you take the sine wave, the function y equals sine x from 0 to pi, the area under one loop of the sine function is exactly equal to 2. It's really a very, very lovely fact. Now, what we're talking about here is a function which is non-negative, and in general, the definite integral from a to b of a function f of x dx, the function is not necessarily non-negative. Part can be above the x-axis, part can be below the x-axis. So this integral is the area above the x-axis minus the area below the x-axis. That's the geometrical meaning of the definite integral. What are some properties of the integral? These are just general properties that make it easy to compute certain integrals. So we have the following property. If we have the integral of the sum of two functions, f of x plus g of x dx, that's the integral of f of x plus the integral of g of x. if we take a function f of x and multiply it by a constant k, the integral of k times f of x is k times the integral of f of x. And these two rules are true both for definite integrals and indefinite integrals. So if this were integrals from a to b, I can just put these upper and lower limits of integration in. And for a definite integral, if you have a, b, c, and you take the integral of a function f of x from a to b, and the integral of that same function from b to c, and you add them, you get the integral from a to c of f of x dx. So these are properties of the integral that are very lovely and used all the time. They're quite important. So we've used the first fundamental theorem of the calculus, and it's called the first fundamental theorem because there is a second fundamental theorem. And the second fundamental theorem says the following. So second fundamental theorem of calculus. Suppose we have a function y equals f of x, and there's the graph. Let's say this is x equal a, and this is, say, x equal b. So the area under the curve is the integral from a to b of, let me use a different letter for the variable, it doesn't matter, f of t dt. And suppose we keep this a fixed, but we let b vary. So instead of calling this b, just to emphasize the fact that it can vary, I fix a, I take a number x, and I look at the integral from a to x. And I call that function capital F of x. This is a function of x. And the second form of the fundamental theorem of calculus says the following: if capital F of x is defined in this way, then if I differentiate capital F of x, I get little f of x. So this function is an antiderivative of little f of x. This is the second fundamental theorem of calculus. An equivalent way of saying this is the derivative of f of x. That's the derivative with respect to x of the integral from a to x, f of t dt. And the second form of the fundamental theorem of calculus says that that's equal to f of x. So what's a simple example? If you have the integral from 0 to x of cosine t dt, and we call that capital F of x, then f prime of x is equal to cosine of x. Suppose we didn't know that. Suppose we just wanted to, well, we can do it directly. So this is a kind of a check. The antiderivative of the cosine of t is the sine of t. So the integral from 0 to x of cosine t dt is equal to sine of x minus sine of 0. Sine of 0 is 0. This is sine of x. So sine of x, this is what capital F of x is. So f prime of x is the derivative of the sine, which is the cosine. So that checks. That's just what we got. All right. Let's look at a somewhat more complicated problem. Suppose we have the following integral. The integral from pi over 2 to x cubed cosine t dt. And this is what we will call my function f of x. And what we want to do is to find the derivative f prime of x. Now, if we had x instead of x cubed as the upper limit of integration, the derivative would just be cosine x. But we don't have x here, we have x cubed. So we need to look at this as a composite function. Suppose we let g of x, or let's say maybe g of u, be equal to the integral from pi over 2 to u cosine t dt. So f of x is g evaluated at x cubed. So by the chain rule, df dx is dg du du dx. What is dg du? This is just cosine of u. U is x cubed. What is du dx? 3x squared. So this is equal to du dx, 3x squared, times the cosine of u, which is 3x squared times the cosine of x cubed. That is using the second fundamental theorem of calculus. Again, all of this is review. This is material that was in the last month of Math 175, and we use it all constantly. I should mention just one other important definition. Sometimes you have things which behave wildly, and what you ask is not what the value is somewhere, but maybe what the average value is. And there's a definition for the average of a function f of x on the interval, the closed interval from a to b. The average is defined to be 1 over the length of the interval. When you go from a to b, this distance is b minus a, so it's 1 over the length of the interval times the integral from a to b of f of x dx. And the average value of a function is something that we will use several times in Math 176. Okay, so we are going to follow the syllabus very closely. And what I've just been talking about is lesson 1 in the syllabus on the fundamental theorem of calculus. So that is the end of this lecture. And lecture 2 will be on the technique of substitution to solve an integral. So this is it. Thank you all.